Hello and welcome. Thank you all for coming to join us tonight. This is our first in the public lecture series in Earth Sciences. And again, welcome on behalf of the Department of Earth Science and the James A. Baker III Institute for Public Policy. We're really pleased that all of you could be here with us. We'd like to extend our gratitude to the Shell Oil Company Foundation, who has sponsored this lecture series as a form of public outreach. And we are grateful to them for that. And we would also like to thank Dr. Alan Levander, Dr. Andre Droxler, and Dr. Jerry Dickens, who have been involved in the development of this program from the get-go. I'm Stephanie Shipp, also from the Department of Earth Science, who's been coordinating this program. We would like to thank as well Ambassador Dirigian and Dr. Lane and Captain King for their assistance in developing this program and helping us move it forward. And as well, we would like to thank the Environmental and Energy Systems Institute for their help. And now I would like to introduce someone who is going to introduce our speaker. We are going to start with Dr. Neil Lane. Dr. Lane is a Baker Senior Fellow and also a university professor here at Rice University. He is going to be our final speaker in the series, and I thought nothing could be better than starting off the series with Dr. Lane's remarks. Thank you.
Thank you very much, Stephanie. Good evening, ladies and gentlemen. I'm delighted to be able to stand in for Ambassador Ed Dirigian to welcome you to the Baker Institute and to have the opportunity to introduce our distinguished speaker this evening. And I was also asked to say a word or two more about the series. Rice University and the Baker Institute are particularly pleased to host this series of lectures. It's really just one way that the university and the Baker Institute can join with the Houston and Gulf Coast community in exploring issues together that are of concern and of interest to the general public. Global climate change is certainly such a topic. There are several reasons, I think, for that. First, the science is very challenging. It's highly multidisciplinary, and it's absolutely fascinating in my view. There have been extraordinary research advances in the last decade or so, and more are being made every day. While there are uncertainties, some significant ones, about the science, the experts in the field are reaching consensus about global warming. Namely, the world is warming, the climate is changing, and will continue to change. And scientists are beginning to agree on the reasons for this change and the reasons they believe what they do. Also, the implications of the scientists' predictions for people's lives, especially in the developing world, but also right here at home, are simply enormous. And finally, the American people, indeed people all over the world, are very interested and are very concerned about climate change. Hence, it's a very hot political issue. Before I left Washington, one of the many hearings that I was involved with on climate change was one called together by Senator John McCain. And you may remember he ran for president at one point. And what he said when he introduced this hearing was, and I was a little nervous about kind of a hearing I was going to get with Senator McCain, given the political tensions over this matter. But what he said was, when he was out on the campaign trail, he was often approached by people, particularly young people, and they said, "Senator, what's your view about climate change? What do you think about it? What are you going to do about it?" And he said, "I didn't know. I don't know what it is. I don't know what to think about it." So I promised the people that when I got back to Washington, I was going to find out what was going on. So we had a wonderful hearing and brought a number of outstanding scientists there. And it simply reflected what the surveys show, namely, people are very, very interested in this topic. This public lecture series will allow us to hear from some of the top researchers in the field of climate science, including our distinguished speaker this evening. In these 5 lectures scheduled for the series, we will learn about what the geological record tells us about past climate changes. We'll examine what the scientists predict for the future. We will investigate how past cultures have been influenced by global climate change. And finally, we hope to explore how our own society might respond to predicted climate change. So we hope you will, and your friends and family and colleagues will join us for all of these lectures. So now it gives me great pleasure to introduce our speaker for this first lecture, Professor Lonnie G. Thompson, who is with the Bird Polar Research Institute at Ohio State University and is himself a leading figure in the field. So let me just read you a few quick items, very much abbreviated from his extensive bibliography. Lonnie was born in Huntington, West Virginia, got his bachelor's degree in geology from Marshall University in 1970, got his master's and doctorate in geological sciences from Ohio State, his PhD in 1976. Lonnie Thompson is one of the first scientists to warn that global warming is causing the glaciers to recede, based on his research from ice core samples from glaciers in the tropics. He's a glaciologist, a distinguished glaciologist. He made his first expedition to glaciers in 1972, in December that year, to Antarctica, which, as you know, is their summer. Balmy down there. I've made 3 trips to the Antarctic. I can imagine that in 1972 the facilities were not even as wonderful as they are today. He was there as a graduate research student. Lonnie Thompson's been on more than 30 glaciological expeditions. He served in NOAA National Panel on Climate Global Change in 1994 to 97. He was invited to breakfast in 1994 by Vice President Al Gore, who you know is very concerned and is very concerned about these issues. He has been on CNN and honored by Time Magazine as America's Best in Science and Medicine 2001. He's made a climatology fellow of the American Geophysical Union 2001. He's the 2001 Distinguished Scholar from Ohio State and on the advisory board of the International Glaciological Society in 1999. He's published over 160 paleoclimate history articles, including 12 in the magazines Science and Nature, probably the most widely read scientific literature that we have in any field of science. The title of Dr. Thompson's talk is Understanding Global Climate Change Perspective from Earth Science. Please welcome Dr. Thompson.
Thank you, Neil Lane. It's my pleasure to have an opportunity to speak to you tonight about glaciers and climate. And what I'm trying to do is to place it into a bigger picture, why it's important to understand what's happening, how we do it, looking at the ice core archives, and then looking at on a global scale, what are happening to glaciers today. And then I'd like to conclude with some of my own opinions on why it is we do what we do and when we do it. So with that as an introduction, I want to start by really introducing the real workers. I've gotten a lot of recognition over the last few years, but it's really a team effort. And if you look at the team, this is the team at Ohio State, and if you look at these names, you'll see that it's an international team. They come from many different countries, and we have now conducted research in over 15 countries in different parts of the world. And without our colleagues in these countries, the work with the logistics and all the permits that you need to do this type of activity, what you will see would not have been possible. I want to start with a couple quotes from the father of glaciology, and this is over 150 years ago, and he said it was important to study nature and not books, and then try to strive to interpret what really exists in the real world. And I think this message holds today, that you need to go out and look at what's going on in the Earth's environment, and you need to do it on a global scale. And a lot of parts of the Earth have been neglected for a very long period of time. If you look at the drivers for climate change and Earth system science, it's really us, the people on the planet. This is sometimes referred to as a J curve. This is the number of us on the planet, and the fact that this number has been increasing on an exponential curve, and that we know there's a limit. There's a limit to how many people this system can support. We don't know what that limit is, but it's out there. And with our today's technology, you can really view the footprint of man on the planet from space. If you look at this view, NASA satellite view of the Earth on November 27, 2000, this is the lights from the activity of man on the planet. And most of those lights are being fueled by the burning of fossil fuels. And so when you look at the scale of our fingerprint on this Earth, it is, to me, not surprising that we would be changing the climate and many other systems on the planet. We know that, for example, CO2 is increasing in the Earth's atmosphere, and we have our records of this, measurements from 1958 from Mauna Loa coming up to the present, and we know we're up to about 370 parts per million by volume. And the ice from the polar regions has provided us a very long perspective of this change. Ice is one of our few archives on the planet of the atmosphere of the past. This is simply a cross-section of an ice core. You can see the crystals, but you can also see the capsules of air from which we can measure some of these important greenhouse gases from the past. And that record now extends back over 420,000 years from Vostok in Antarctica. And this shows the general variations over that period of time of CO2, methane, and the temperatures as reconstructed from deuterium measured on those cores. If you look at the big picture, there's a very high correlation between these greenhouse gases and temperatures on the planet. The other thing that you see, it's very striking, is that there's a rhythm and a cap to the maximum. If you look at the CO2 curve here, we never get over 300 parts per million by volume, and we never get below about 180 parts per million by volume. We don't understand what it is in the natural system that puts this control on this, but this is what happens in the natural system. And then if you bring this up to the present and you overlap it with where we are today, this is the last glacial cycle, and the decrease in CO2 coming into the Holocene. In 1900, we passed 300 parts per million by volume. We're now at 370, and 60 years out, we will most likely be over 600. And the reason for this is very simple. If you look at energy policies in the U.S., we have a plan to bring on a coal-burning power plant to provide power one a week for the next 20 years. You go to Beijing in China, where we've worked every year since 1994, and you go to the government there, you get the same plan to meet the power needs of that growing economy. So this may well turn out to be an underestimate of the rate at which CO2 increases in the atmosphere. Our temperature record for the planet is shown here based on instruments, and we know 2001 came in as the second warmest year in record. And it's surpassed only by 1998, which was an El Nino year. And if you look at the projections for 2002, it's likely that there will be an El Nino this year. So and El Nino years tend to be warmer years for the Earth. And we know that the 1990s is the warmest decade in this instrumental record. So there's little doubt whether you're looking at this record, instrumental record, or the proxy records that I will be showing you, that the Earth's temperatures are warming. And for the past 30 years, we have been looking at different places on the planet, looking at ice, looking at the record, the archive in the cores, but also looking at what's happening to the volume of ice on the planet at these sites. And what distinguishes where we work is that we have concentrated at the high elevation sites in the low latitudes in the tropics. And this is an extremely important place to look because we have about 50% of the area of the planet in the tropics, between 30 north and 30 south. We have about 70% of that 6 billion people living in this area. And so understanding the natural climate variation as well as potential human impact in this area becomes extremely important. Now, the archive is wonderful. Ice records anything that's in the atmosphere at the time the snow falls. And in some of these glaciers, like the margin of Quelccaya in the Andes, where we have a very strong seasonal precipitation, you can see the wet season and the dry season. And these are 1 meter layers, so you have very high resolution in the record. Now, showing this photograph serves two purposes. It shows the nature of that archive, but it also, this photo was taken at the margin in 1977. In the year 2001, this is bedrock. this ice has disappeared over that very short period of time. The way we recover the cores is just drilling a column of ice through the archive. This is a drilling on Huascaran down in the Andes of Peru. And these cores are brought back frozen, and they're archived many different parts of our environment. And this makes ice core research really interdisciplinary. And an actual ice core is shown here on the right, where you can see this is from western China, the Glia ice cap. You can see the monsoons, the clear sections, the dry sections, and the core. And these are cut, and all these different types of analysis can be made on that core, and then you can reconstruct the environment as well as the climate history in these areas. And we use stable isotopes of oxygen and hydrogen as our temperature proxy. We look at atmospheric chemistry. We can look at the natural variations, and we can see the human impact. You can see the lead, you can see legislation policy to reduce lead in gasoline, and you can see it go down in these ice cores after that. You can look at the net accumulation, how thick those layers are. Very few proxies tell us what the precipitation has been on the Earth in the past. Dustiness of the atmosphere, how deserts have changed, vegetation, particularly in the tropics, pollen in the snow, tells us something of how the vegetation reacted to climate change. The volcanic history comes from the ashes and from the gases, the sulfates that come from the eruptions. It's very surprising how little we know about the long-term history of volcanic activity. Anthropogenic emissions, the greenhouse gases being one of those. And then more recently, we've actually been looking at microorganisms in the cores from these very, very remote, cold, low oxygen environments, because they give us an indication of what you might look for if you were going to the ice cap on Mars or Europa to look for life forms, and then developing the protocol that you need in order to know that what you're looking at is coming from the core and not from the Earth's environment itself. The ice is a very good recorder of climate, and there's some very simple physics of ice that tell us before we drill the length of record we can get from these archives. Three important things: how much snow falls each year, the annual accumulation rate, how thick the glacier is very important in the resolution in the time record. As far as the length of time, the critical factor is the temperature at the ice-bedrock interface. If it's below freezing, time cannot be removed, and therefore you can get a very long record out of an ice cap out of China, even though by Antarctic or Greenland standards, they're very short in length. I want to look at just a few of these records and then work our way forward in time. And I want to start in South America and look at a couple of longer records. If we look at Huascaran or Calcaya or Sahama, all of these received their snowfall coming out of the Amazon basin and ultimately out of the tropical Atlantic. So even though they're on the western side of South America, the precipitation is actually coming out of the Atlantic side. And the records are very high resolution. This is the last 100 years from Huascaran at 9 degrees south of the equator, 20,000 foot elevation site. And you can see the seasonal variations in the isotopes, which is our temperature proxy, the dust annual variations, dry season. The nitrates reflect changes in NOx emissions coming out of the Amazon, which is upwind from this site. So in the upper part of these cores, we have very high resolution annual records. And then the records give us a very long perspective in these areas. And Huascaran provided us the first ice recovered from the tropics that was deposited during the last glacial stage, when we had the large continental ice sheets. And the amazing thing about the record was this very large increase in dust, which is consistent with the polar cores, but an isotopic shift of about 6 parts per mil, which is identical to what we find in Greenland and in Antarctica. And yet this is 9 degrees south of the equator. And if you look at this curve, you can see the late glacial stage here, early Holocene warmth, cooling the little ice age here and the warming as you come into the present period. The nitrates reflect vegetation changes, less vegetation in the upwind sources during the late glacial stage, more in the early Holocene. And then the dust record, and I'll point this out, this big event about 4,000 years ago stands out as the biggest dust event in the last 17,000 years in this tropical site. And I'll come back to that a little later. You can come forward in time and look at the relationships between cultures in South America and the climate. And from the layer thicknesses, we can calculate things like the precipitation and how that's varied through time. And this is a decadal record from 470 AD coming up to the present. And when you look at that, you can see dry and wet periods. And then if you look at the anthropology, the archaeological records from this part of the world, you can see a relationship when these cultures are growing and decreasing as you go through time. Quelcaya is on the Altiplano in southern Peru, and when it's wet in these highland areas, we get highland cultures developing. And when it's dry in the highlands of South America, we get the coastal cultures in northern Peru and southern Ecuador developing, and they're out of phase. And the interesting thing about this is over centuries, but it's the same thing that happens in this part of the world today when you have an El Nino. You get the precipitation in the coastal deserts, and you get drought in southern Peru. And it would suggest that there are larger scale variations in the climate system. The beauty of this is our recorded record from this part of the world started in 1531 with the arrival of the Spanish. And the ice provides us an annual record of what was going on in the climate when these cultures, pre-Spanish cultures, existed in this part of the world. If you go further south, you get into the drier parts in the subtropics to Sajama. This is the highest mountain in Bolivia. The summit elevation here is 21,500 feet. You can see it's very dry today. And the records from the summit are remarkable in that in the upper part, you can see those seasonal layers. You can see the dry seasons and the wet seasons in the core. But they're also remarkable in what they preserve. And in these cores, you find insects like Heteroptera. This is perfectly preserved. It comes from 110 meters down in the core. And you can identify the species, and then you can send it off and have an AMS date done on it, so you can help constrain the time scale in the earlier part of these records. And we have done that using multiple dating techniques. And just to give you an idea of how a time scale is developed for an ice core, you can count layers, those annual layers, back until they get too compressed to resolve them. In the upper part, you can use the bomb horizons like tritium from all the thermonuclear bomb tests to give us a timeline. Where we have historical documentations of eruptions, we can get timelines from that. And then from the insects and the plant remains, we can get carbon dates. And on this core, we were very fortunate right at near the bottom, a meter above the bottom, to have enough material to get AMS dates from two different labs, which show that this core starts about 25,000 years before present. And you can look at that record, and you can see the detail in the top where you have the high resolution, and you can see how it smooths as you go back in time, as time gets compressed. But you can also see the glacial maximum, the bowling warming period that we see in the northern hemisphere, the cold reversal, and the warming in the Holocene. And the cores allow us to also look at what's going on in the environment. The chemistry here comes from the salars in the Holocene. When the lakes dried up on the Altiplano, you have these huge salt flats. And when you go back in time, you can actually see in the glacial period, these periods when the lakes were full and that salt source was cut off. And in this site, in the subtropics at 18 degrees south, unlike the polar cores and unlike in the deep tropics where Huascarán is located, there's an 8-fold decrease in dust concentrations during the glacial maximum. So you really do need a global perspective to reconstruct the climate of the past. The other surprising thing about the Sajama record is because we do have time resolution, and we can look at 50-year changes in the isotopes, which is a temperature proxy for Sajama, and we can compare it to a core from Greenland that's annually dated through this period of time. And that's the red GIS-2 record that you see here. The remarkable part about this is that if you look at the isotopic shift, the glacial maximum, 5.4 parts per mil at 70 degrees north of the equator. At 18 degrees south of the equator, 5.4 parts per mil. You get in the cold reversal, you see the same type of shift, and as far as we can tell from the timing, the timing is synchronous. And this tells us a lot about how the climate system works. It shows a very dramatic temperature rise taking place over a very short period, less than 40 years, in the natural system. And some people will take this and they'll say, well, that just goes to show you that the system changes very rapidly on its own. So how do you know in the 20th century that the changes you're seeing are not some natural change taking place in the system? But I look at this, and what it really tells me is the system is very sensitive to change, natural or perhaps human-induced, and it can change quite rapidly over a very short period of time. Now, I want to come forward in time and look at what's happening and kind of put together a global picture. And I want to go now to Africa, to Kilimanjaro. Kilimanjaro is 3 degrees south of the equator. It's the only place in Africa to get an ice core record because it's of the elevation of 5,895 meters. It's also a place that undergoes tremendous changes during El Nino, which links a lot of these tropical records around the planet. It's very wet during the warm phase of an El Nino and generally very dry during the La Nina phase. And so this is one of the potential archives in this record. The other thing that's unique about Kilimanjaro is the photographic history of the ice on the mountain. This photograph was taken in 1912. And this is the western breach here. But you can see where the glaciers come down on the mountain. And these photographs go forward in time. This one at the top was taken in 1970 by Bruno Messerli. And you can see how much ice was on the mountain in 1970. And this is a photograph that we took in the year 2000 when we were drilling the ice field. And you can visibly see the change of ice on the mountain. Well, it turns out there's also a history of maps for these ice fields, and they go all the way back to 1912. And the light blue area shows the extent of ice in 1912. The dark blue shows the extent of ice in 1989. And part of our project, we had aerial photos flown of these ice fields. And I'll point out the northern ice field here. You can see these lobes, and you can see that it was a solid mass in 1989. By the year 2000, February 16th, when we had the aerial photographs taken, you can actually see the northern ice field, the lobes are gone, and there's now a hole that is developed in the center of that ice field. And from these aerial photos, we have made a map. The white area shows the ice extent in the year 2000. And these stars show the areas where we recovered cores to bedrock from the remaining ice fields on the mountain. Now, if you take the area from these maps, it's just a simple calculation of the area of ice, total area on the mountain from 1912, when there was 12.1 square kilometers, and you come up to the year 2000, where there's 2.5 square kilometers of ice, and then all the maps in between, you get this linear line of decrease. And you can project that into the future, and if you do that, the ice fields on Kilimanjaro will disappear sometime between 2015 and 2020 if things stay the same as they've been in the 20th century. This is not saying that the Earth's going to get warmer. If they just stay the same, these archives will disappear. So there is a real need to get these records. And we have a view of probably what the last piece of ice will look like on Kilimanjaro. This is what's left of the eastern ice field. And you can see that these glaciers actually sublimate. And if you look at this, the margins of this thing is actually layered. It has a stratigraphy in it. So the ice fields are definitely disappearing under the present climate on the mountain. Well, the reason we go for the ice core is to try to put that into perspective. I mean, the first photo was taken in 1912. Well, we need to have a longer-term perspective to understand what the significance of those changes. And to drill here, beyond the 25 permits that we needed to go there and recover the ice core, we also had to hire 92 porters to move the 6 tons of equipment that we require to drill and to transport frozen ice core back down the mountain up to the summit. If you get on the summit of Kilimanjaro and you look at the northern ice field, you can see the ice mass is there, and it's one of the few glaciers that you can see the entire sequence on the cliffed margin of the ice field. You can see the camp here, and you can see the drill dome where we're drilling. We drilled 3 cores to bedrock from this northern ice field. We have a lightweight drilling system, what was engineered, designed, and built at our center that allows us to break it down and carry it up to these high elevation sites and then assemble it. It's powered by solar panels that are out on the surface of the ice field. And it's an electromechanical drill, so it physically cuts the cores. And in drilling, you can actually see events as you go back in time. And one of the striking events in this core is this event here. And we now know this occurred around 4,000 years before present. It is the most distinguished event in the core as far as in the chemistry and the dust. And the interesting thing about this event is it's the same time as the event that we saw over in Huascarán in the tropics of South America. And the question is, what was it? And the other interesting thing about this part of the world, this is where civilization, as we know it, developed. There's the Egyptian written record that goes back over 6,000 years. And if you look at the writings on the sepulchres at this time, and back then the leaders at the end of their realm would write the history of all the good things they did, kind of like our leaders do today, except in this period, 4,200 years ago. And the scripture reads that there was widespread starvation, that there were actually sand dunes marching into the Nile River. And people were migrating to the north and south looking for food. And people were actually eating their children at this time. And there are several different documentations of this in different parts of Egypt. So you have a lot of confidence that this actually took place. And this dust event here, and if you talk with Harvey Wise up at Yale, the Akkadian culture collapse, you look at Peter Domenical's cores in the Gulf of Oman, biggest dust event in the Holocene at this same period of time. So major event had implications to cultures and societies on a large scale at that time. Now, timing on getting ice core records becomes very important, and particularly here on Kilimanjaro. One of the ways that we get a timeline at the top, you need to know where you are, where your record begins. And this was a problem on Kilimanjaro. Our timeline comes from looking at the chlorine-36 spike that comes from the Ivy test that were done in 1952. In the early days of testing, we actually set off one of these tests in the ocean, and it produced radioactive chlorine-36 that goes around the world. And in all these sites where we've drilled, we've been able to identify that layer, and because we know when the test took place, we have a timeline. Now, when we drilled in the year 2000, this event was 2 meters below the surface of the northern ice field. And as part of this project, we put in a satellite-linked weather station on the northern ice field. We also have accumulation stakes. Those were remeasured in February of 2001. And the surface had lowered on the northern ice field 109 centimeters. If we get the same ablation taking place this year, February, this timeline will be lost. And we would not have had a way to fix the top of the climate history here. So the ice there is definitely disappearing. Well, how about the other parts of the world? We've spent a lot of time working in China, and I'll just show a couple of these sites. Around the rim of the plateau, the highest place drilled to date, Dasupu, 7,200 meters, 23,500 feet. Very cold place. It's 28 degrees north of the equator, but it's a beautiful site too. This is Shishabamba in the background, which is 8,014 meters, the drill site here. And the cores are quite remarkable in that, like many tropical records, you can actually see the annual layers, the monsoons, the dry seasons, monsoons and dry seasons in the core. Now, each of these records present a challenge on getting the cores and getting them back from the other side of the world and keeping them frozen. And for these, just to give you an idea of how they come from the top of the Himalayas, these are yaks, and these are insulated core boxes, and we can get 6 meters of core in one of those boxes, so we can get 12 meters on a yak. We drilled 476 meters of core, and so I'll give you an idea of how many yaks you need to conduct a project like this. And the mentality of a yak, the most similar thing that I can compare it to is a cat. If you ever tried to get cats to go in the same direction down the mountain, it can be a challenge. But the Tibetans have a way of working with them. But once they get back to the lab, we can see this beautiful annual oscillation of the monsoon system. We can see, in this case, the radioactivity coming from the Soviet test in 1962. So we can go into an area where we have no accumulation records, identify the bomb horizons, calibrate the signal, and then we can date the core back in time. And when we do that for this site, we can go back with annual resolution back to 1440 AD. And these are the annual values of our temperature proxy, isotopes, the dust, chemistry, chloride, nitrate, and sulfate. And I'll just point out a couple features. First of all, this event here, 1790 to 1796, major monsoon failure. In 1792 in India, over 600,000 people died in the north-central part of India from this event. This was also a major El Nino event. And so one of the things you need to know is what is the natural occurrences of these events in the past. And you can imagine the impact of this today. The population of India last year went over 1 billion people. This same event, natural event occurring today, would have a tremendous social economic impact. As you come forward in time, you can see the increases in nitrates and sulfates. This is due to industrialization going on in India and Nepal, which is upwind from this site. And you can also see the enrichment of the isotopes as you come to the present. In fact, the last 50 years are the most enriched in this annual record back to 1440. Now, you can push this record back in time. If you look at the Cato averages of the isotope record for the last 1,000 years, you can see the last 50 years are isotopically the most enriched in that period of time. And you compare it with the temperatures and precipitation. And we published this in Science last year, but we didn't publish the whole record. Because if you look at the whole record, what you see, as you see in this curve, looking at the last 9,000 years, that isotopically the last 50 years is the most enriched in the history of this ice field. And you can see the methane, this is the first methane curve to come from a non-polar glacier. And you can see the anthropogenic increase at the top of this record. You can see the levels in the Holocene. So the reason we didn't publish it was, can you reproduce it? Is there something unusual about this site, even though it's the coldest, highest place we've ever drilled outside of the polar regions? And the temperature at the base of this ice field is minus 13.8 degrees C. So the whole record should be there. Well, if you look at what's happening to temperatures in Tibet today, temperature records, instrumental records don't go back too far, 1961. There are 178 stations around the Tibetan Plateau, and this is a diagram that shows them by elevation as you go higher on the plateau. This is the number of stations at these different elevations. So at 4,500 meters, we have about 3 stations. But when you look at this, what you see is as you go higher on the plateau, the temperature increases are greater, and suggesting that you're getting a greater response at the higher elevation sites. Well, we can take the ice cores and we can say, well, what do they show? Because they come from the very highest places on this plateau. And if you do that to those 3 sites, and you look at the isotope Cato averages for the last 1,000 years, you can see 1,800 going back to 1,000. In this period, there are events occurring in one part of the plateau that really don't stand out in other parts of the plateau. But by the time you get up to 1,800, you see an enrichment taking place at all these sites, and the greatest enrichment taking place at the highest elevation site at the top of the Himalayas. Very consistent with what we see in the short-term instrumental records for this part of the world. Now, last fall, we went into central Tibet, the most remote place we have drilled to date. It's right in the center of Tibet, this Puragangri ice field, and we recovered 3 cores to bedrock. This is a fascinating place. There are no roads into central Tibet. We had 6 six-wheel drive trucks, 4 land cruisers, 48 people on the expedition. We had a company up in Pennsylvania that provided us with these Atura mats so that when we crossed old lake beds, we could lay these down to keep the trucks from breaking through and sinking down to their axles. And we went into this very remote area. There you can see the sand dunes in the center part of Tibet. These sand dunes, the sand moves in the spring. So when you look at the margin of this ice field, you can actually see those layers when the sand moves. And a tremendous stratigraphy, very well dated. And this is really what you need in a climate record. You really need to be able to put it in time. And when you go up on the margin of the ice cap, you can actually see the annual layers like steps. These are about 65 centimeters high, and you walk up some 2,000 of these to get up on the flat part of the ice field. And once you're up on top, it's a very large, it's almost like what you would see in Antarctica or some other part of the world. Well, these cores are currently being analyzed, but we have an overview of the isotopes. And this is the isotope record from the surface to bedrock. And if you look at this, you can see the mean values. And again, for this site, you can see the most enriched values occurring in the last 50 years, the very most recent part of the record, duplicating what we saw further south at the top of the Himalayas. So suggesting that the changes in this part of the world are unusual. Now, the last place I want to look as far as what's happening is ice is go back to South America, where we have our longest documented records. And this is from the Quelccaya ice cap. This is the first tropical ice cap ever drilled. It's the only real ice cap, tropical ice cap on Earth. And back in mid-1970s, it covered 55 square kilometers. And that's the site where that margins view was taken. Oh, I'm sorry. Somebody. But we've been able to document the changes that are taking place. And to show this, this is a boulder about half the size in front of the stage here in the margin of the ice field taken in 1977 when that margin shot was taken. By 1979, you can see the wall moving back from the boulder. And as you come forward in time to 1995, you can see the boulder setting out here and the ice retreating. And then by the year 2000, you're looking at the end of that boulder, looking out towards the ice field. You can see the lake that's formed in here, and you can see the wall continuing to march up to higher elevations. And you can get a good sense of how much ice has been removed from this site. This is the boulder here that was being pushed in 1977, and there was a 20-meter wall. So all this ice in here has melted out, and the ice is retreating. And we've been able to put some numbers on that by looking at the largest outlet glacier coming off of Quelccaya, which is Koikelis, is here. The boulder is located in here. And back in 1978, we set up a survey line to photograph this outlet glacier, not to look for any evidence for global warming, but to monitor what happens to a tropical glacier through time and under present climate conditions. And this was a photo of that glacier that was taken in 1978. And you can see it's a healthy glacier, convex, there's a few little ponds in front of it. But as you come forward in time, by the year 2000, there's a 62-acre lake in front of that glacier. And by August of 2001, you'll see that that retreat continues. The ice is gone from the lake. And we've been able to actually map that and the changes. And if you look at the series of photographs as you come through time, and you start with the first aerial photographs in this area taken in 1963, you can map the margin and the change that's taken place. And from 63 up to 78, the rate of retreat was about 4.7 meters per year. From 78 coming up to 83, it was up to 8 meters per year. 83 to 93, 14 meters per year. 93 to 95, 30 meters per year. 95 to 98, 47 meters per year. And 98 to 2000, it was up to 155 meters per year. That's 1.3 feet per day. So you can almost sit there and watch this retreat taking place under the current climate conditions in this place. And you wouldn't be too concerned about this if this was the only glacier in the Andes that was behaving in this fashion. But the power company, Electro Peru, has been monitoring glaciers up in the Cordillera Blanca, and this is a whole series of retreats. You can see in the late 70s that really an exponential increase in the rate of retreat, and the green here is the Corycalis there. So it's very large scale, and they're concerned about it because power production in their hydroelectric power plants in the dry season is now down to like 20% of capacity. And as the ice fields, which are really natural dams that store precipitation from the wet season and then release it in the dry season, as their area shrinks, the water resources, not only for the hydroelectric dams, but for irrigation, for municipal power sources, for Lima, Peru, all those things are put under stress. And the case for what's happening to the glaciers extends far beyond Peru. You can go down to the tip of South America, and you can look at the photographs of the glaciers in this area taken in 1945, 1998, and you can see how the retreat is taking place. And as you move northward toward the equator and Calcaya, you can see photos here taken in 1949, a photo in 1994. You can see the cliff in here, waterfalls, as the ice retreats. And as you come to the northern part of the Patagonia ice field, photo taken in 1896 and a photo taken in 2001 showing the retreat of the glaciers. So it's very clear the glaciers are giving a very consistent story, and you can look at the 20th century on a global scale. And the red areas here show documented retreat taking place over this period of time. And if you look at this, you can already see there's only one place, this blue area up in Norway and Sweden, where glaciers are actually advancing as you come toward the end of the 20th century. And the reason for that is believed to be that storms that used to bring the snow into the Alps and feed the glaciers there have a more northerly track, so the snowfall has increased on these glaciers. Even though the temperatures in that area have increased, precipitation is overriding effect on those glaciers. So very dramatic changes taking place. And if you come back, the question you say, okay, what are the drivers here? Well, if you look at the temperature curve, based on all of our proxy records and then overlap with the instrumental records, you can see this hockey stick profile and this very dramatic change in the 20th century. And then you look at some other possible forcings. You can look at the CO2 curve for the atmosphere over this period of time. And then you can look at the emissions, where this CO2 is coming from, fossil fuels, land use changes, and you see this curve. But the disturbing thing about the curve is that it doesn't matter what label you put on this. You could put loss of biodiversity. You could put population. The impact of humans on the system is such a large scale. Then you ask, gets more into philosophy or thinking on the subject, how do you make a change? And who pays the price for the change? When this report of the loss of ice on Kilimanjaro came out, there was a debate in the parliament in Tanzania by the Minister of Tourism, essentially saying that she did not believe Thompson's theory that the ice on Kilimanjaro was going to disappear. Well, there's no theory to it. I mean, it's just mapping what has happened in the physical world and projecting that into the future. But the real driver, and the reason she was saying that, is that she was trying to raise funds, international funds, to build a series of hotels at the base of Kilimanjaro. And if there's no ice on Kilimanjaro and people aren't coming to see the ice on the equator, that may hurt the ability to raise funds. And often when we look at the drivers of the decisions that we make, it comes down to dollars and cents. And then you have to ask the question, okay, who, and you could make an argument, and someday I guarantee some lawyer will make this argument, that Kilimanjaro is the #1 foreign currency earner for the government of Tanzania. The fact that the ice is disappearing on Tanzania probably has very little to do with what the Tanzanians are doing, but it has to do with what's going on in the rest of the world. And you ask, who's responsible for that? And who pays the price? Well, unfortunately, I think the people who will pay the price first for climate change will be those who are least capable of dealing with it. And these are the people who are already living in marginal areas like the high elevations of the Altiplano in South America. These people have no resources. We're very fortunate to live in a country where we have resources, and when we decide to change things, we can. But many places, that is not an option. But even here, you have to ask what might happen. And we have some indications in the recent past. You can look at things like the 1995 heat wave, showing the areas where temperatures were over 104 degrees Fahrenheit in the U.S. for a sustained period of time. Night temperatures were high. 600 people died in Chicago. And you hear about people, but if you went out to these areas and you looked at the livestock holding pools, this is what you would see in the same period of time, because life on Earth has developed in a certain temperature range. And there are people like Paul Epstein at Harvard that are looking at mosquitoes whose metabolism is keyed to the mean temperature and their feeding habits. You take a mosquito that's infected with malaria, you raise the temperature, it means the metabolism of the mosquito goes up, it has to feed more often, and therefore it can infect more people or other organisms in its normal life cycle. So life on Earth and temperature and knowing the linkages in the system becomes a very critical issue. And so the last point I would make has to do with people in general. I don't think we in the U.S. are different than people in other parts of the world, and why we make change. And you can look at the environmental history in this country. You can look at soil conservation. You go back and you look at Hugh Bennett, and the father of soil conservation. In the 1920s, he was in Washington telling him there was a real problem with our farming practices out in the West, and the people listened. There were congressional hearings. But in 1931, he was in Washington, and a friend called from Chicago. There was a big dust storm. 12 million tons of dust fell on Chicago. The same system was headed toward Washington, D.C. He delayed his committee meeting so that right in the middle of the presentation, the dust hit Washington. And immediately, there was a 180-degree change on this issue. And I look at the state of Ohio, Cuyahoga River. I mean, we knew it was polluted 15 years before it caught on fire. But we didn't do anything until it caught on fire. It had to be a crisis. I mean, somehow this had to come up on the top of the burner. And now we have game fish in that same river. So we can make a difference if we choose to. And I think there are a lot of other evidence in the system that we don't often know what's happening. I mean, it's amazing to me that if you look at the fall of the Soviet Union, and you look at our reports, our intelligence reports, you look at what was going on in the Soviet Union in the 1980s, no one was predicting the collapse of this system. But it's like one morning people woke up, and everyone from the peasants in the fields to the leaders in the country realized this was unsustainable. This system doesn't work. And it changed. And I think often, if you look at the history of man and how we behave, that's what happens. And you can look at languages. And we've worked in China every year since 1984. And my daughter is getting a degree in the Chinese language. She writes and reads Chinese. But it's kind of interesting to look at their version for crisis. Crisis has two characters, the Wei and Ji. And it's interesting it has two characters in the oldest written language of man. The first one, you might expect, Wei means danger. And certainly a crisis brings danger. But the second, Ji, means opportunity. A crisis brings an opportunity to make things better. And it really depends on how we as human beings respond to a crisis that determines the outcome of that crisis. So my feeling on the issue of global warming, we will continue to have meetings, we will continue to talk about it, we'll collect data of the glaciers retreating, and that is the purest data that you can get, because there's no way a politician can argue that the glacier has a political agenda. It is just responding to its environment, and it's disappearing. But will that make a difference? Probably not. What will make a difference is when there is a crisis that pushes the system to suddenly this issue comes to the front burner and we decide to deal with it. So that's pretty much what I had to say, and thank you for your attention.
Did you take a question or two?
Oh, for sure. Yes. Yes.
A couple things. Is there any way to sink as much carbon as you project for the next 40 or 50 years for the anthropogenic? And second, one of your earlier slides, like the third or fourth one, showed a spike in methane at the corresponding CO2 spikes. Is that from the methane ices, either submarine or in the permafrost area?
Well, if you look at the CO2 and the methane curves, there's some differences in those, but if you look at the long-term trends, they're more or less in sync. You get a greater precession signal, precession being the 21,000-year orbital forcing in the methane. And the reason for that is the methane is coming mainly from the wetlands in the tropics, where water is driven by this precessional cycle. If you look at the possible sinks, I mean, could you get rid of this carbon, and could you do it economically? We actually at Ohio State have a group that includes the John Glenn Institute on Public Policy looking at this issue. Ohio, we have a number of injection wells for hazardous waste into saline deposits deep in the strata where you could sequester things for a very long time. And it would be a likely candidate for our 33 fossil fuel burning power plants in Ohio to get rid of the carbon. The cost is in getting it out of the emissions from the plant and getting it in a form where you could inject it. And there are different estimates of how much that would cost, and I've seen figures as high as $1,000 per ton. And then there are other people would argue that you could use biological sequestering of carbon much cheaper, maybe for $10 a ton. But the fact is we don't know, and it would be an expense. I think it's very clear already that there is an expense in doing nothing also. If you go to places like Venice, where they have a real flooding problem, and it's gotten worse as you come into the 20th century, and they have tremendous engineering plans to put in gates that would be underneath the ocean and filled with seawater, except when the winds blow a certain way across the Mediterranean, and they would be pumped full of air, and they would come up and they would keep the seawater out of the town. And the cost for that's estimated to be something like $3 billion. The real cost would probably be more like $15 billion. And then there are other environmental issues that come up, is that the whole city was built with the idea that the sewage system is flushed by the tides coming in and out, and if you shut that off, you have another environmental issue that could be even worse. So sometimes I'm not sure that the dollars and cents will solve some of these issues, but for sure they cost. And you can look at 1998, that year of the warmest records that we had, and you look at the reinsurance companies' cost, $92 billion for various disasters, from hurricanes to major snowstorms, ice storms, and the like. And that was what the insurance companies paid. Most of the damage comes from taxpayers because a lot of things aren't insured. But there's a cost for change in the system, and it's just a matter of where you have the greatest cost. Do you have greater costs if you deal with the issue up front, or you try to tackle it? And I think the biggest problem right now is we're not even trying, being the greatest emitter of CO2 of 25% of the annual budget, and not going to the table to talk about how we might solve this problem is wrong. I'm not saying Kyoto is the way to do it, but we need to be discussing how we do it. And I think also as individuals, we play a role. Next Tuesday, I'll go up to see our Senator Voinovich because next, in February, there will be this Jefford bill introduced in the U.S. Senate for curbing emissions from coal-burning power plants. And it includes mercury and sulfur dioxide, nitrous oxide, and CO2. Now, how many of those things actually get through we'll wait and see. But I do think as scientists, we can present the record of what's happening. And I think there's a little doubt, whether you look at the glacier record or the temperature record or the borehole temperature record or ice extent on this Earth, the Earth is warming up. And you could argue how much of that's natural, how much of it's human. From a science point of view, in our archives, it doesn't matter. The glaciers are disappearing, and that record is disappearing with them. And those archives should be recovered. Because that's our history of the past in these areas. Yeah.
But related to that, in the past you showed 370 parts per million as the maximum CO2. What has controlled that?
Well, the greatest storage of carbon is in the oceans, and it's generally thought to be related to circulation and sequestering of carbon in the deep ocean. But it has to do with productivity in the oceans as the climate system changes, nutrients going in the oceans. But the bottom line is we don't know why it caps. Why does it go only to 370, 380, and why does it only, the low is only 180? Obviously there is a control in the system. And it's only in the 20th century when humans came back and we start mining the carbon of the past, and trees and coal and oil and all that, or just forests that have been archived, and we bring it all to the surface and we burn it and release the carbon, that whatever those natural sequestering systems are, we are currently overriding them with our emissions. And we don't know what the consequences of that will be to the climate system as we go down the road. But it's very clear to me that we will have to deal with climate change as part of survival in the future, simply because of our current policies and the policies of other developing countries. So part of it is going to be adaptation, I think, as we go in the 21st century. Yeah.
Is there a possibility that, in fact, you're losing a large portion of the record during these hottest periods of time by the process of glacial ablation, as you're describing? You're losing some of the recent years and some of the records as the glaciers are retreating very rapidly. Would that tend to, in fact, create these unconformities that might give the appearance of capping temperatures and capping emissions?
Yes, that could. And it's something that we've dealt with this new records out of Kilimanjaro, because all those ice fields formed at different times. The longest record is 11,500 years in the northern ice field, but the southern ice field formed 1,500 years ago, which is kind of interesting because it's the date of the onset of the ice cap Quelccaya down in the tropics in the Andes. But the way we look for disconformities in the record is we drill multiple cores, at least two, usually three, to bedrock, and look at the chemistry, the isotopes in the record. And if there's an offset, then you have to suspect there may be an unconformity. But ice is a very good medium to work with, because in that ice are bubbles. If you've ever had a period of melting in the past, the bubbles are released. And the ice, when it refreezes, is a clear band. And so I can tell you for Sahama and Huascaran and the history of those records, there are no ice bands. Never has the gas been released. It is being released from the top of the ice field, northern ice field in Kilimanjaro today. But there's no, in the 51-meter record, there are no periods where there are no air bubbles in the core, which would tend to suggest that what's happening now is unusual in the history of that ice field. Yes?
Do you have any idea what happened 4,000 years ago?
No. We think it's a drought because we've looked at the composition of the particles in the event in South America. And the composition that you can do with ICP-MS measurements, you can look at all the trace elements. The composition of that dust is exactly what you find in the core of the Andes, which is, in this area, is granodiorite. And the glacier outwash moraines are made of this type of material. And so it suggests a major drought. If you look at the work of Harvey Wise at Yale and Peter Domenicow in the Middle East, a drought that lasted 300 years, a major drought. And the records, documented records in Egypt, or if you go to Kilimanjaro, the composition of that dust suggests that it's terrestrial. I mean, we were looking for things like iridium, some forcing, volcanic. It's drought. It's a normal type of material, only it's very concentrated in this period of time. And then the question is, what caused that event? And we don't know. Yeah.
Yes, you have this rather strange plateau between 1940 and 1980 in the rise of global temperature. During this period, are your glaciers in tropical countries receding, or are they do they also have this plateau in the recession?
Well, one of the problems is the documentation, the actual observations, measurements of the retreats. Some of the longest records are those in Peru, where the power company, and this is another trend that's going on, the power company used to be a government power company. It's now privatized, and the first thing they stopped was monitoring the glaciers. So those measurements stopped in 1996. And it's also interesting, they sold the power plant, the Rio Santa power plant, to a group of American and Chilean investors in 1996. Because they have this long history, they know what's happening with the power production. But the lack of observations, but every place, whether you're looking in the Ruwenzori mountain range in Uganda, or you look at the glaciers on Mount Kenya, where Stefan Hassenrath has mapped these, the retreat is taking place, and where you have time-lapse photography, there's an acceleration, particularly in the lower elevation glaciers. And I think this is something that's very important to point out. If you look at Kilimanjaro, you see this line, linear line of retreat taking place. You go, and part of that is that it's at 5,895 meters. It's higher in the Earth's atmosphere than Kilkaya, which is down at 5,600 meters. And if you look at the models for temperature changes in the tropics, you see the zero isotherm moving up in the atmosphere. So you're going to see the greater effect in the lower elevation sites. And gradually, if this continues in the future, then you'll see an acceleration at higher elevation glacier sites as you go in the future. But you can go to countries like Venezuela. 1972, they had 6 glaciers. Today, they have 2. Probably in 10 years, they'll have none. And then this gets into other issues of what's the role of ice on the planet as one of the balancing factors controlling the temperature of the Earth. A lot of energy right now is going into melting these glaciers, whether they're in the tropics or in the high latitudes or the Arctic sea ice. That's a big energy sink. What happens when that sink it becomes greatly reduced or no longer out there? Do we lose one of our natural control on the temperatures on the planet? And I don't think we know the answer to that question either.
Take a couple more questions.
Okay.
Yeah, are there any places where there are reversals of this trend, such as the upper atmosphere? Doesn't some of the some of the satellite data show that upper atmosphere temperatures have gone the opposite way?
That's an important question. The stratosphere has actually been cooling, and this is something you expect with global warming. But the difference between satellite temperatures and surface instrument temperatures, something that's been debated at the National Academy. And as they've looked at these, it's now both curves show warming. It's just that surface shows more warming than the satellite images or satellite data. And but you have to remember they're not sensing one place. They're sensing an area of the atmosphere. And And there are many different satellites that make up that time series. And yeah, is it the same? Are you looking at the same place in the atmosphere? That becomes an issue. But we have taken temperature records on Kilimanjaro. You look at the reanalysis data, which uses satellite and instrumental data, and you can look at 500 millibar level in the Earth's atmosphere. And if you look at that, you see the oscillations and you see a slight warming. But if you look at temperatures at the base of Kilimanjaro, Jean Altman at Princeton, who's been studying baboons in a national park there since 1971, and she's been measuring maximum and minimum temperatures every day since 1971. She's got this tremendous record, and when you plot that out, you see a 3-degree warming at the base of the mountain in this national park over that period of time. And and I'm sure part of that has to do with land use changes in the region, different albedos and things, but certainly a warming trend taking place, and certainly the glaciers on top of Kilimanjaro seem to be agreeing with the near surface measurements. Yes?
Taking the view of 100,000 years, there have been periods when all but the Antarctic and perhaps the Greenland glaciers have indeed melted away. Looking at this longer record, have you brought that into your work?
For sure, and I think this the fact that the temperature of the Earth has been warmer in the past is true. I mean, we have a lot of geological evidence for that. We also have a lot of evidence for abrupt changes occurring in the system, natural system, over short periods of time. But I don't think we can take much comfort from that because the difference is that there weren't any people or very few people on the planet when these changes took place. Certainly a natural change of that magnitude would have tremendous disruptions of any society that existed. But the difference today, and I think even if you look at natural variations that occurred 150 years ago in Europe, you have crop failures, what people do? They migrated to the New World where we had a lot of land that wasn't too densely populated. But when you look at that view of the Earth and the lights at night today, and you say, okay, you have a disruption in a place like Bangladesh, and you know, there are projections of what if sea level rises 0.5 meter over the next 100 years. In a place like Bangladesh, you displace 100 million people. Where do those people go? And who pays for it? And who are they going to displace? I mean, but I think that's the difference between today and looking at these records in the past. Yes.
Yes, I had two more detailed questions. You talked about, I think in Tibet or in the Himalayas, a 50-year time period approximately, where there was a greater change in the isotopes at the higher elevations and then less as you went down.
Yes.
Do you have an explanation for that?
Well, we have some theories. One of the things you might be seeing is the loss of snow cover. A lot of energy, if you had lots of snow in the high elevation plateaus, a lot of energy would go into removing that. But once the snow is reduced, then that energy goes into heating the atmosphere and raising the temperatures at those higher elevations.
And the second, also mentioned that this one place in Norway, there was more snow and the storm tracks had changed. Has anybody followed that up? I mean, there certainly are records of meteorological records going back there, so you could look at 50 years in storm tracks and see.
Oh, yes, and this is what's happening in that area. There's
So
more
somebody's
precipitation.
actually published something on it?
Yes, they have.
Oh,
Yeah.
okay. Thanks.
I think there's enormous interest here. Maybe we take the last question.
Okay.
I had a question. If whether or not anthropogenic or natural variation is causing the global warming, are there any ways, I mean, have there been proposals about how to change or reverse, or will the Earth naturally reverse itself or go back to the way we think is normal? Or are there any ways besides just reducing carbon emissions? Has there been any research in that, or?
Yeah, I think that those are important questions. If you look at, you can look at the worst case scenario. What if we burn all the fossil fuels we have? CO2 will go up to 2,200 parts per million by volume in the Earth's atmosphere. Temperature likely to spike, and 10 million years from now, temperatures will come back. the carbon will be sequestered back in the oceans and the system, and we'll take care of the problem. The real issue is what happens to people in this period of transition. But the other thing, the thing that I find most disturbing, when the retreat of Kilimanjaro came out, Boston Globe had a cartoon and had a Detroit, and there's a guy reading the paper saying, it's the snows, the ice on Kilimanjaro is disappearing. And here's the executive behind the desk saying, Kilimanjaro, what a great name for an SUV. But there's a message there, and I think the biggest problem we have right now is that we're not even trying. I mean, we're not even trying to deal with this issue. I mean, we can get around without SUVs. We know that. So the drivers are other things. But what you can do about it, there's a lot of technology coming along. Fuel cell technology using hydrogen, I think it has tremendous potential. You could use solar power in Nevada where the sun shines a lot to separate hydrogen from water, transport the hydrogen to places where you can't use that, and provide a clean fuel for the future. And the fact is, our fossil fuels are all limited, and you'll see different times on when they'll run out, but USGS says oil, 30 years, natural gas, 100 years, coal, 220 years. We're going to have to change to another energy source if we're going to maintain the economy in the future. And why not start working on that now? And why not make some policies that would limit the changes that we're making in the atmosphere until we do better understand how the system works? I think it's very important.
This has been a wonderful kickoff. There's enormous interest here. We could go on all night, but perhaps we shouldn't let our speaker rest and come down and meet him on your way out. And please join me in thanking Dr. Thomas.